On this page, we'll talk about the hypothesis test for a difference in two population means. The general steps of this hypothesis test are always the same. As expected, the details of the conditions for use of the test and the test statistic are unique to this test, but similar in many ways to what we have seen before. The first step would be determine the hypotheses. The hypotheses for a difference in two population means are similar to those for a difference in two population proportions. The null hypothesis, H sub 0, is again a statement of no effect or no difference. So we would say that H sub 0, the null hypothesis, is that the two means, the population mean for one is minus the other, you subtract them, you get 0. In other words, they're equal to each other. The alternative hypothesis, however, is saying that one's larger than the other or they're not equal, as shown here. Either the first, well, the difference between the two is negative, that means the second is bigger than the first, or the difference between the two is positive, that means the first is larger than the second, or that just the difference between the two is not 0, meaning that the difference between them is significant. They're not the same number. Once we state our hypotheses, then we'll collect the data. As usual, how we collect the data determines whether we can use it in the inference procedure. We have our usual two requirements for data collection. Samples must be random to remove or minimize bias. Samples must be representative of the population in question. We use this hypothesis test when the data meets the following conditions. First, the two random samples are independent. The variable is normally distributed in both populations. If this is not known, samples of more than 30 will have a difference in sample means that can be modeled adequately by the t-distribution. Lastly, let's see, if we scroll down, let's see, as we discussed previously, t-procedures are robust even when the variable is not normally distributed in the population. If checking normality in the population is impossible, then we look at the distribution in the samples. If the histogram or dot plot of the data does not show extreme skew or outliers, we take it as a sign that the variable is not heavily skewed in the population, and we use the inference procedure. Notice that this is the same condition we used for the one sample t-test previously. The third step would be now we're going to assess the evidence. If the conditions are met, then we can calculate the t-test statistic. The t-test statistic has a familiar form. T is equal to, here, let's zoom in so we can see it better. It is the sample statistic minus the hypothesized population parameter divided by the estimated standard error. But we will not expect you to calculate it. Instead, you will use StatCrunch. If you're curious, here's the formula for the t-test statistic, because it's quite a formula. T is equal to the observed difference in sample means on the numerator, so that's not so bad, minus the hypothesized difference in population means divided by standard error. In other words, the standard error is kind of a complicated formula. It's the square root of the first standard deviation squared divided by that population size, n1, plus the same for the second population, the standard deviation squared divided by that population size, n2. So it's not a simple formula. We'll just use StatCrunch. In real life, people would use applets or calculators or computers to calculate these things. They would never do them by hand. So that's what we'll do as well. Okay, now let's scroll down. Now that we've kind of seen the formula, we know we won't use it. We kind of know what it looks like. So we know what StatCrunch is doing, but we'll use StatCrunch. As we learned previously, the t-distribution depends on the degrees of freedom, df. In the one sample and match pair case, the degrees of freedom is n minus 1. For the two sample t-test, determine the correct degrees of freedom is based on a complicated formula that we do not cover in this course. For this reason, we will use StatCrunch for all these calculations. The fourth step would be state a conclusion. To state a conclusion, we follow what we've done on the hypotheses test. We compare our p-value to a standard level of significance. If the p-value is less than or equal to alpha, we'll reject the null hypothesis in favor of the alternative hypothesis. If the p-value is greater than alpha, then we fail to reject the null hypothesis because we don't have enough evidence to support the alternative hypothesis. As always, we state our conclusion in context, usually by referring to an alternative hypothesis. Now, step 3 is to assess the evidence. If the conditions are met, then we calculate the t-test statistic. It has a familiar form, okay, t is equal to sample statistic minus hypothesized population parameter over estimated standard error. That comes out to a complicated formula. As we learned previously, the t-distribution depends on the degrees of freedom. So degrees of freedom equals n-1, as we've seen before. And then I think we saw this already. To state the conclusion, we follow what we have done in our other hypothesis test. We compare our p-value to a stated level of significance. If the p-value is less than or equal to alpha, we reject the null hypothesis in favor of the alternative hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. We don't have enough evidence to support the alternative hypothesis. As always, we state our conclusion in context, usually by referring to the alternative hypothesis. So now I'll look at another example about context and calories. Does the company you keep impact what you eat? This example comes from an article titled Impact of Group Setting and Gender on Meals Purchased by College Students. In the study, researchers examined this issue in the context of gender-related theories in the field. For our purposes, we look at this research more narrowly. Step 1 will state the hypotheses. In the article, the authors make the following hypothesis. Quote, the attempt to appear feminine will be empirically demonstrated by the purchase of fewer calories by women in mixed gender groups than by women in same gender groups, unquote. We translate this into a simpler and narrower research question. Do women purchase fewer calories when they eat with men compared to when they eat with just women? Here the two populations are women eating with women, population 1, and women eating with men, population 2. The variable is calories in the meal. We test the following hypotheses at a 5% significance level. So alpha is 5%. Okay. The null hypothesis is that the mean difference in calories is equal to 0, meaning the number of calories a woman eats when she's with women is the same as that if she's with any men. But in this case of in the alternative hypothesis, we're assuming she eats fewer calories than if she's just with men and women versus if she's with only women. So the mean number of calories she eats when she's with women, if we say that's 1, so they're saying, yeah, population 1 is that, like, if she's eating with women only, we're assuming that she's eating more, supposedly, and then population 2 is mixed genders, or just at least one man is there, which is the same as saying that the mean number of calories that she eats when she's with women only is more than or greater than the number of calories she eats when she's with a mixed gender. Okay, so as it says, mu1 represents the mean number of calories ordered by women when they're eating with other women, and mu2 represents the mean number of calories ordered by women when they were eating with men. Note, it does not matter which population we label as 1 or 2, but once we decide, we should have to stay consistent throughout the hypothesis test. Since we expect the number of calories to be greater for women eating with other women, the difference is positive if women eat with women is population 1. If you prefer to work with positive numbers, choose the group with the larger expected mean as population 1, because you'll be subtracting a smaller number from a larger number, which would give you a positive number. This is a good general tip. Our second step will be to collect data. As usual, there are two major things to keep in mind when considering collecting the data. First, that samples need to be representative of the population in question. Second is that samples need to be random in order to remove or minimize bias. What are good representative samples? The researchers state their hypotheses in terms of women. We did the same, but the researchers gathered data by watching people eat at the Hub Rock Cafe on the campus of Indiana University in Pennsylvania during the spring semester of 2006. Almost all of the women in the data set were white undergraduates between the ages of 18 and 24, so there are some definite limitations on the scope of the study. These limitations will affect our conclusion and the specific definition of the population means in our hypotheses. So random samples, we'll think about that. The observations were collected on February 13th, 2006 through February 22nd, 2006, between 11 a.m. and 7 p.m. We can see that the researchers included both lunch and dinner. They also made observations on all days of the week to ensure that weekly customer pattern did not confound their findings. The author states that since the time period for observations and the place where they were observed were limited, the sample was a convenient sample. Despite these limitations, the researchers conducted inference procedures with the data, and the results were published in a reputable journal. We'll also conduct inference with the data, but we will also include a discussion of the limitations of the study with our conclusion. The authors did this as well. Now, did the data meet the conditions for the use of a t-test? The researchers reported the following sample statistics. First, in a sample of 45 women dining with other women, the average amount of calories ordered was 850, and the standard deviation was 252. In a sample of 27 women dining with men, the average number of calories was 719, and the standard deviation was 322. One of the samples has fewer than 30 women, so we need to make sure that the distribution of calories in the sample is not heavily skewed and has no outliers, but we do not have access to a spreadsheet of the actual data. Since the researchers conducted a t-test with this data, we will assume that the conditions are met. This includes the assumption that samples are randomly selected and independent. Step 3 now will be to assess the evidence. We use StatCrunch to conduct the sample t-test. Two sample t-test summary hypothesis. Mu1 is the mean of population 1. Mu2 is the mean of population 2. Mu1 minus mu2 would be the difference in the means. And we said that our null hypothesis is that the difference is equal to 0. Our alternative hypothesis is that the difference is greater than 0 or positive with pooled variance. And then this is what was spit out by StatCrunch. Note that we will not require you to calculate the test statistic by hand or to use an applet to find the p-value. If you are curious, here's the formula for computing a test statistic. Our population 1 this time is women eating with other women, so the sample mean is 850 for the, and then the standard deviation for the first sample where women were only eating with women is 252, and n, the number of women in that first sample where women were only eating with women is 45. And the population 2 is women eating with men. So the sample statistic there, x2 bar, is 719. The standard deviation of that second population is 322. And the number of women in that sample was 27. So if we were to use the t-test statistic, this is the formula. It's pretty complicated. So as it says, we wouldn't do that by hand, but just in case you're curious where the formula comes from, the formula for determining the degrees of freedom is even worse than that. It's more complicated. So we'll leave these calculations to StatCrunch and focus instead on drawing conclusions. And then step 4 is actually state a conclusion. Okay, the general conclusion here is the hypotheses for this test are that the alternative hypothesis is that the difference in the means is 0. The alternative hypothesis is that the difference in the means is greater than 0 or positive. Since the p-value that we got from StatCrunch is less than the significance level, it was 0.0358. That's less than alpha in decimal form, 0.05. Yeah, because it said P was, well, the StatCrunch gave us 0.0385. That's less than our alpha, the significance level. So we're going to reject the null hypothesis and accept the alternative hypothesis. So in context, to state that in context, at this university, the mean number of calories ordered by undergraduate women eating with other women is greater than the mean number of calories ordered by undergraduate women eating with men. So now I'll make a comment about conclusions in general. See, in the conclusion above, we did not generalize the finding to all women. Since the sample included only undergraduate women at one university, we included this information in our conclusion. But our conclusion is a cautious statement of the findings. The authors see the results more broadly in the context of theories in the field of social psychology. In the context of these theories, they write, quote, our findings support the assertion that meal size is a tool for influencing the impressions for others. For traditional age, predominantly white college women, diminished meal size appears to be an attempt to assert femininity in groups that include men, unquote. This viewpoint is echoed in the following summary of the study for the general public on National Public Radio, NPR. It says, both men and women appear to choose larger portions when they eat with women, and both men and women choose smaller portions when they eat in the company of men, according to new research published by the Journal of Applied Social Psychology. The study conducted among a sample of 100 college students suggests that both men and women are influenced by unconscious scripts about how to behave in each other's company. And these scripts change the way men and women eat when they eat together and when they eat apart. Should we be concerned that the findings of this study are generalized in this way? Because in that study, they just said, or not, sorry, in that, in NPR, they said that women do this instead of just saying that women at this college in this age group do this. But the authors of this article address the concern, including the following disclaimer for their findings. They say, while the results of our research are suggestive, they should be replicated with larger representative samples. Studies should be done not only with primarily white middle-class college students, but also with students who differ in terms of race, ethnicity, social class, age, sexual orientation, and so forth. This is an example of good statistical practice. It's often very difficult to select truly random samples from the populations of interest, so researchers therefore discuss the limitations of their sampling design when they discuss their conclusions. In the activities that follow, you will have the opportunity to practice parts of this hypothesis test for a difference in two population means.